Hello dear students, in this particular unit we are going to study properties of matter. Fine, I am writing elasticity. It is a topic that we are going to study later, but first we are going to start from properties of matter. Before attending this lecture, I would like to suggest all of you to go through the note that I have already uploaded. That note is very introductory in nature. The topics you have already studied in your HS level. Fine. So if you want to revise the things, you can go back to your NCERT books. Okay, NCERT books that you have already with you, I hope. Okay, so NCERT physics books you should never throw out. Okay, always keep them. This is a must. NCERT books. So basically, since you are into physics now, so you should take care of especially about the physics books. So is the properties of matter. Let us start with. So if I say matter, we always consider like solid, then liquid, and then gas. Okay, so in this particular unit number 4, we are going to discuss all these 3 types of matter. Okay, the properties of all these 3 types of matter. So let us first start with solid. Fine. Okay, so you might have seen that that solid, liquid, and gas. Okay, all of them to a greater or less extent, okay, more or less, they try to conserve. They try to conserve means they don't want to change, isn't it? They try to conserve their shape and size. Okay, or you can say in detail that configuration. Okay, so if I ask you that, suppose you have a ball made up of steel. So if you want to change the shape, will you be possible? Will you be able to do that? No. Okay, so the steel ball, in case of steel ball, it is not that easy to change the shape or the size. Okay, so that means it is very difficult to change the configuration of a steel ball. Okay, so that you can say that the steel ball or a solid, even if you consider a wooden ball or you can consider a rubber ball, to more or less extent you can say that they do not allow the change in shape and size so easily. If you want to change them, you will have to apply some force. So that is one nature. In case of liquid also, but in liquid there is a tendency, but it is not that great. Okay, so in comparison to solid, it is very less. Okay, it is there, but it is very less. So that it also shows some kind of resistance to the change in the shape and size, but that change resistance is named by some word that we will discuss later. And similarly, in case of gas also, we can expect some kind of they try to conserve something, but it is not successful fully. And these two things together, they are called fluid. Okay, fine. So as I told you that, let us start with solid. Okay, so you know that solids are very tightly bound, is it? Like this. Suppose these are the molecules. Okay, now this is a molecule, this is a molecule, so they are tightly bound to each other, isn't it? Like this. Okay, there will be another one like this here also. Yes, in this one here. Okay, it is a representation, right? So you can see that this molecule is attracted to this molecule and they are properly bound to each other. Okay, this is bound to, they are bound to each other, this is bound, this is bound, this is again bound to this one also, this is bound to this one also, like that. So here, so molecules in a solid are tightly bound, okay, to each other through a intermolecular, I can say, binding force. Okay, so this intermolecular binding forces keep the molecules close. Okay, and you can see the gap. Okay, this is the equilibrium. Okay, it will not come closer because of the equilibrium distance. At this distance, the intermolecular binding force is balanced. Okay, so that means at this stage the molecules are in minimum potential energy state. Okay, fine. So that is called equilibrium. Whenever you see that they are anything in equilibrium, and then you can say that they are not at all excited, they are not at all disturbed, then you can say that they are in equilibrium. The distance is not going, the distance within them have been fixed and it is not going to reduce. So that means they are in equilibrium and they are said to be in a minimum potential energy state. And it is, you know, that everybody in the universe tries to be in a minimum potential energy state. That is the truth. Okay, this is a law. Now suppose that, okay, then you want to increase this distance. Okay, like this, you just want to increase the distance between these two molecules. Okay, distance between these two molecules, you want to do some change. Okay, you want to bring about some change. Okay, so what we are planning to do, you will apply some force in this direction. Okay, so when you apply the force in this direction, what will happen? This equilibrium will be disturbed. Okay, the equilibrium gets disturbed, and this force is basically because of the application of this force. Okay, the distance between these two things will increase. Okay, so that means it was this normal position, isn't it? But because of the application of this force in this direction, what happened? It changed from normal. So that means it got what? It got deformed. Okay, deformed means disfigured. Okay, it was suppose anything that is supposed to be in a particular shape, it has been changed. Deformed means it has changed. Okay, and this deformation happened because of this force. Okay, so this is called deforming force. Fine. Now this deforming force is nothing but what? Action. And you know that every action has an equal and opposite reaction. Okay, so since a action has been applied in this direction, an equal and opposite reaction will be created in this direction. Okay, within the body. Fine. Now this equal and opposite reaction produced within the body because as a reaction to this deforming force is basically called what? Restoring force. So this is a restoring force. So what is a restoring force? This is the force which is creating inside the body as a reaction to the deforming force. So you see, as you have seen that as you wanted to increase the distance between these two molecules, so you applied a force in this direction. This force is called deforming force, and as a result of this, the body got deformed. Okay, now and because of this action, there will be reaction produced inside the body. So as soon as you release this force is removed. Okay, then what will happen? This particular thing, the two molecules which were in excited state, because you see, initially I told you that when there are no force is applied, they are in equilibrium. So what happened? Their potential energy is a minimum potential energy state. But when you have stretched them out, you have done some work on the body, you have done some work on the molecules, and which has increased their energy. Fine. So the molecules have now energy which is more than the minimum potential energy. That means they are not in equilibrium state. Now they want, so as I told you that everything in the world wants to be in a minimum equilibrium, minimum potential energy state. So as soon as this force is released, what will happen? the molecule will try to go back to its original position. Okay, this molecule will try to go back to its original position. Fine. And to bring back the initial distance between them. Listen to me very carefully. Okay, so when you release this force, then what will happen? They will try to come back to its original position, but then also they will have to do some work, isn't it? So they will come back to their original position by at the expense, by using the extra energy that has been supported, given by this force. Okay, that the work, extra energy that has in terms of the work done by this additional force, sorry, the deforming force. So while going back, the molecules will use that extra energy to do work to go back. Okay, so that means the force generated in this direction during this course of action is called restoring force. Okay, so restoring force, and so we have got to know about two terms, that is deforming force and restoring force. I would again like to tell you about it. See, suppose these two molecules, okay, they are bound to each other, they are also bound to other molecules. Fine. So you applied some force in this direction, so this is deforming force, is it? So when you applied this molecule came to this position. Sorry. Okay, you just applied this, in this molecule came to this position. Okay, so what will happen? Initially the distance between them was this. Now the distance between them is this. Is it? So when it was at this position, it was in a minimum potential energy state. Minimum energy. Okay, but when it came to this stage, what will happen? The force has done some work on this particular molecule to stretch it, isn't it? So work done is nothing but energy. So it has, this work is done on the body, fine, by the force. So now at this stage, the energy is not minimum, it is minimum energy plus something else. So it has more energy. Okay, and this energy is given by nothing but the work done by this deforming force. Are you getting? So at this stage, the molecule is in the excited state because it has more energy. So as I told you that everybody in the universe wants to go back to the minimum potential energy state. So it will try to get rid of this. Okay, so how to get rid of this? It will again go back to its initial position. So while going back, the molecule will have to do some work. Okay, earlier work was done on the molecule, now molecule will have to do some work, and it will do some work. To do work, what you need energy, and from where this energy will be taken? From this extra energy that has been supplied by the deforming force. Okay, so during this course of action, a reactional force is created, that is called restoring force. Okay, now the thing is that, suppose that this is a molecule, this is the molecule, they are attached to other things. Suppose that the deforming force is equal to restoring force, is exactly equal to restoring force. Then what will happen? Okay, then what will happen? The molecule will go back exactly to its initial position. So suppose it has come back or come to this position. If F deforming is equal to F restoring, okay, then what will happen? It will go back to its initial position. Okay, and the body will retain its original configuration. Only original configuration means shape as well as size. Fine. But sometimes what happens, they are not equal. Okay, deforming force may not be equal to restoring force. Means suppose you have if you have stretched the molecule up to this, okay, but the restoring force created is not equal to this. So will it go back to its initial position? No, it will stop somewhere here. Okay, so it will create a permanent deformation. Are you getting? So if they are not equal, then there will be a permanent deformation in the body. So two things, see, if both the forces are equal, then what will happen? It will come here and it will go back. Okay, So there will not be any change, permanent change. Okay, so that is one case. And another case, what will happen if the deforming force is not equal to restoring force, then what will happen, it will come here. Okay, but when it will try to go back, because while going back it will use restoring force, so it will not go back totally, it will stop here only. Okay, so there will be a permanent change. Okay, so this type of materials in which this deforming force is exactly equal to restoring force, and there is no permanent deformation created, that is called elastic material. Okay, so elastic material, if you ask for examples, you know that steel. Can you change a steel easily? No, there is no permanent deformation created. Okay, similarly iron. Okay, if you want to change the shape and size of iron, you will have to apply lot of force. Okay, similarly if I consider rubber is also elastic. Okay, because if you stretch it, it's okay, but if you release it, it will come back to its original shape size, is it? That is called rubber. Okay, and this case where permanent deformation is created because restoring force is not equal to deforming force. Okay, so that material is called plastic. Okay, plastic material, like you know that like putti and atta dough, you know that now, if you make a dough of this atta or flour to make chapatis, so you can give it any size. Okay, it will take it, it will not never come back to its original position. You can't make chapatis out of rubber, you can make chapatis out of atta only, or this flour only. So that kind of thing, yeah, or you can say that glass or any wooden thing, that is also plastic. That means there will be a permanent deformation. So till now you have learned about deforming force, then restoring force. Okay, and then you have learned what is elastic material and plastic material. Okay, so if I talk about elastic material, that means that there is a tendency in every solid to conserve its shape, size or configuration. Okay, so that tendency or that property of a material is called elasticity. Okay, so in here the first topic of our unit 4 is elasticity. Fine. So elasticity, whenever we talk about elasticity, it will be basically about solids. Okay, but elasticity has other types also applicable for liquids and gases that I will discuss here in detail. Now another term that you need to learn, I think already you know about it, that is called strain. Okay, already all of you know about it. Okay, so you see, as I told you, that when you apply the deforming force F deform, and what happened, they changed, is it? The position has changed, so that means it has got deformed. Okay, whatever, there is a change in the initial configuration, so that change is nothing but strain. Okay, so how do you calculate it? Suppose there is a rubber wire like this. Okay, fine, so it is fixed on this side on a wall. Okay, and you are stretching it in this direction with a force F. Okay, so what will happen, initially the length is L, you increase its length and it has become thinner, and the length increased to this. Okay, so this is del L. So final length is nothing but, final length after deformation is del L. So if I ask you what is the strain produced, then what you will have to write, change by original. Fine, so change. So if you if I ask you about now, change can be in many ways. Okay, if you consider a wire, then we basically talk about a change in what, length, okay, then there will be a change in the volume also. How? Because if it is a cylindrical pipe, what is the volume? Volume is pi r square into L, okay. So if L is changing, volume is also changing, isn't it? So there may be different kinds of changes. That is, so if it is the change in length, then it is called longitudinal strain, okay. So that is nothing but del L by L. We will write like this always, and remember that during the course all of us will represent the same notations, okay. You are not going to write something else, okay. We will write like this, or sometimes we can write it like this also, okay. Del L can also be written as small l by capital L. Don't worry about it. Similarly, if you have volumetric strain, this is similarly, what is that? Change by original. So change in volume divided by original volume. All of you know about it, I hope. So this is del V, okay, del V by V. You can write it as small v by capital V. So remember, there is a change. If I write small v means this one, not like this. This is not small v, okay. Be careful. If you write like this, it will be totally zero, okay. Small v capital V doesn't mean that v in small or big size, remember. So if you write like this, be careful. If you write like this, it will be v by v equal to 1. So that is totally wrong. You will get 0 for this. Always write small v like this, okay. Give a curl, okay. So this is the volumetric strain, fine. Next, about shear strain, okay. Another kind of strain is there, that is shear strain, okay. Suppose that you have a box like this, fine. I know all of you have studied it already, but these are just revision of all the things that you have already done, fine. So suppose that I have applied a force like this, okay, in this direction, fine. So before that, I would like to tell you that deforming forces can be of two types, okay. All of you know about it, I know. Deforming forces can be of two types. One is called normal, another is called tangential, is it? So deforming force, normal force or tangential force, similarly, so here what is happening, we are applying the force tangentially, okay. So when we apply the force tangentially, what will happen, and keep the lower face fixed, okay, then what will happen, it will shift like this. So it will go like this, isn't it? So you can mind one thing, that here there's no change in size. It is basically the change in the shape, okay. It is basically changing the shape. There is no change in the size here. We are just changing the shape, okay. So that means see, it is no longer a cube now. Earlier it was a cube, now it is no longer a cube. So that particular strain is represented by shear strain, fine. So here if I consider this change, okay, how far it has traveled, say del x, okay, and this length to be capital L, then shear strain is basically denoted by theta, okay. So this angle is called theta. You understand, this is nothing but shear strain. Now if you consider this triangle, if I consider this to be A, B, C, so this is the right angle, isn't it? So tell me this, if I consider the triangle A, B, C, tan theta is nothing but what? Perpendicular by base. What is it? Perpendicular. This is a base, is it? And this is a perpendicular. Perpendicular means del x, and this is a base, okay. So since you see, these are basically, we are talking about solids, okay, and it is basically like wood, it is basically like steel, iron. So in practical cases, this angle is not that much. Suppose that you have a steel cube. Do you think that you can stretch it that much? You can strain it that much? No, the strain will be so less that the angle is supposed to be very, very small. You can't even see it with naked eyes, okay. You will have to take microscope, traveling microscope type of thing, then only you can calculate this. And this will be like 1 degree or 0.5 degrees, so less, okay. So if theta is less, you know that if theta is small, then what happens? Tan theta is approximately equal to theta, because sine theta is approximately theta and cos theta is approximately what? 1. Tan theta means sine theta by cos theta means theta by 1. So if theta is very small, so tan theta can be written as theta, so it is equal to del x by L. So this is the formula for shear strain. So remember, so longitudinal strain and volumetric strain is basically about change in the size, okay, but shear strain is basically about the change in the what? Shape, okay. That is why it is represented by theta, okay. So theta is nothing but del x by x. So here you see we have discussed first deforming force, restoring force, elastic material, plastic material, then elasticity. Then we have studied about strain, 3 types of strain, and also we have studied that deforming force is of 2 types, for normal force and tangential force, okay. And in these 2 cases normal force acts, okay. See, if you want to change the length of the wire, you cannot stretch it like this, isn't it? You will have to stretch it like this, means the force is perpendicular to this surface, so this is called normal force, fine. So similarly here the force is acting on the surface, so tangentially, so this is called tangential force. So in these 2 cases it is basically normal stress, but in this case it is basically the tangential stress or tangential force. So that's all for the introductory class. Thank you so much.